Welcome to another lecture about cryptography. In this lecture, I'm going to go over the details of asymmetric cryptography and I will focus on the RSA algorithm. Here is the outline of today's lecture. First, I will introduce the asymmetric cryptography and define a number of terms. Then we will see that asymmetric cryptography is used for confidentiality or secrecy as well as authentication. And an example of using um, public key cryptography or asymmetric cryptography to provide authentication would be digital signatures, which we'll see them in near future. Also, in this lecture, I'll talk about the details of RSA and the arithmetic behind RSA, which motivates us for using elliptic curve cryptography. We will see the pros of RSA and the drawbacks of RSA and the complexity of RSA that makes us use ECC or elliptic curve cryptography. There are a number of misconceptions about public key encryption or asymmetric encryption. I'm just going to mention a few of them here. The first thing is some people think public key encryption is more secure from the cryptanalysis and all the crypto attacks compared to symmetric encryption. That's of course not true. Also, there's another myth which says public key encryption is a general purpose technique that has made symmetric encryption obsolete. That's definitely not the case. Also, there's a feeling that key distribution is trivial when we're using public key encryption, while key distribution and the key distribution centers for symmetric encryptions are very hard to deal with. Well, that's not also true. Now let's take a look at some history about public key crypto systems. The concept of public key cryptography evolved from an attempt to attack two of the most difficult problems associated with symmetric encryption or the traditional way of encryption. The first one was key distribution. The problem was how to create a secure communication without having to trust a third party, which is basically the key distribution center. And another problem with symmetric encryption was digital signatures, which means how to verify that the message comes intact from the claim center. Basically, digital signatures will solve the problem of authenticating a message. Uh, those were the open problems before public key encryption or public key crypto systems um, become popular. But in 1976, Diffie and Hellman from Stanford University achieved the breakthrough that was completely different from the previous approaches in cryptography. They came up with a solution to digital signatures and key distribution that was very important. So let's talk about a few terms about public key crypto systems. The first thing is plain text, which we saw it in symmetric crypto systems as well, which is basically the readable message or data that is fed into the encryption algorithm as input so that we can convert it to the ciphertext. Another term is encryption algorithm, which performs various transformations of the plain text to create the output of the algorithm, which is the ciphertext. Another term here is the public key, which is used for encryption or decryption. Another term is private key, which is used for encryption or decryption. And the difference between private key and public key as the name can tell, is that private key is assumed to be private, but public key is basically a shared information for public to see. And I'll talk more about this later. Then ciphertext is the scrambled message produced as the output of encryption algorithm. And then decryption algorithm is an algorithm that accepts a ciphertext as an input, and also it accepts a key, either a private key or public key, matching key, to produce the original plain text. Let's look at this figure, or these two figures that illustrates how public key encryption works. Imagine you have two parties, Alice and Bob, and they are going to use RSA, which is a public key crypto system, in order to provide either confidentiality or authentication or digital signature. Let's first see an example of confidentiality. Imagine Bob wants to send a message to Alice, and Bob wants to send the message in the form of a ciphertext so that no one at the middle of the way can eavesdrop the message or sniff the message and can find out what Bob is going to tell to Alice. Now, what are the assumptions here? We assume that Bob knows Alice's public key, which is here represented by PU sub A. As you can see, that's Alice's public key. And also, Alice has a private key that only she's aware of it, and nobody else has the private key of Alice. As the name of private key can tell, no one has access to Alice's private key except Alice. So let's see how Bob can create a confidential channel and send a confidential message to Alice. Imagine the original message, the plain text, is X, and Bob wants to send X to Alice, but not in plain text, in ciphertext. What Bob does is it executes or runs the encryption algorithm, which in this case we assume is RSA, and on the plain text X using the public key of Alice. So think of an encryption algorithm like an algorithm that gets two inputs. One is the plain text, one is the a key, in this case the public key of Alice. And the outcome is represented this way. As you see, y equals E of PU sub A comma X. PU sub A is basically the public key of Alice, and X is the plain text, and Y becomes the ciphertext that we're going to transmit to the other side. When Alice receives Y, which is the ciphertext, she's going to apply her private key, which is PR sub A, on the ciphertext Y, and basically it runs Alice is going to run the decryption algorithm on the private key and Y to reconstruct the plain text X, right? And now you can see why this is going to be a confidential message exchange, because only Alice can reconstruct the plain text, because everyone else is not aware of what private key of Alice is, and the ciphertext Y can only be decrypted in a feasible fashion and in a limited time by using the private key of Alice. And if you don't have the private key of Alice, it would be either impossible or very, very hard to decrypt Y and create X. That's the first part. That's basically the concept of providing confidentiality using public key cryptography. The second one is the concept of digital signatures or authentication. Imagine Bob wants to send a message to Alice, but in this case, in part B, Bob doesn't really care about confidentiality. Bob cares about authentication and wants to do something that Alice knows that the message that is received by Alice is coming from Bob and not anyone else. So basically, Bob wants to sign the message and send it over to Alice, so Alice knows only Bob can send this message. So what Bob needs to do is to give the plain text message that wants to be signed and Bob's private key, which is represented by PRB, PR sub B. B stands for Bob and PR stands for private key. It applies the private key of himself and X, which is the plain text, on the encryption algorithm. Let's say the encryption algorithm is the RSA and it needs plain text and a key, in this case Bob's private key. And the encryption algorithm is going to create a ciphertext. That ciphertext would be Y, and Y is basically the encrypted version of X if we use the key private key of Bob. And that ciphertext will be transferred to the other side. That's basically the signed form of X. And when Alice receives that signed message, which is Y, Alice can apply Bob's public key, which is PU sub B, which is assumed to be available to anyone because everyone has public key of everyone else. So Alice is going to have the public key of Bob. So Alice is going to apply the decryption algorithm on Y and uses public key of Bob to decipher or decrypt Y and reconstruct the original message X. Now, what's missing in this picture, which I'm going to add right now, is that when we're going to use the public key cryptography for digital signature, we are going to send X along this signature Y. And when you send both X and Y to the other side, when Alice uses public key of Bob to construct X, Alice can compare that X with the X that is given in the same message as Y, and then it compares these two. If they are equal, then that means the message X was signed by Bob. If they're not equal, that means the message is not authenticated, so Alice knows that Bob has not sent this message. Now, another small detail that you need to know in this part B for digital signatures is that when the sender of the message, Bob, wants to sign a message like X, normally it doesn't sign the original message because the original message can be very long, and applying the encryption algorithm like RSA on a very long message would be time consuming. So what Bob does is he applies a crypto hash function like one of those SHA hash functions on X, and then the resulting message digest lowercase x will be used for digital signature. And basically Y would be the encrypted message digest, not encrypted X. And when the receiver of the digital signature, which is Alice, wants to verify the signature, basically Alice is going to do the same thing. Alice will have the value X. Alice will apply the hash function, the same hash function on X, and create the message digest of X, and then Alice basically compares that message digest with the deciphered or decrypted version of Y, and then if they're the same, that means the signature of Bob has been verified. So this is an extra thing that wasn't given in this picture. I just wanted to clarify it a little bit. Let's quickly compare the conventional versus public key encryption. In conventional encryption, what we need to have is the same algorithm or the same key for both encryption and decryption. That's why we call it symmetric encryption and or symmetric cryptography. And also the sender and receiver must share the algorithm and the key for this type of cryptography, and also in order for this symmetric or conventional encryption to be secure, we need to keep the key that is shared between the sender and receiver secret. Also, it must be impossible or at least invisible to decipher or decrypt a message if the key is kept secret. Moreover, the knowledge of the algorithm and the samples of ciphertext must not be enough to find out the key, because otherwise, the hackers can guess the key, and the whole security of symmetric encryption will be in danger. Now, in the public key encryption or public key cryptography, we need to have an algorithm that is used for encryption and a related algorithm for decryption with two keys, one for encryption and one for decryption. The sender and receiver must each have one of the two matched pair of keys, not the same one. So if you have two keys, one should be given to sender, one should be given to receiver. And one of the two keys must be kept secret, otherwise there would be no security in this public key cryptography or crypto system. Also, it is impossible or very hard to decrypt a message if one of the keys are kept secret. And knowing the algorithm and knowing one of the keys, which is going to be the public one, plus the samples of ciphertext or encrypted messages, should not be good enough or should not be sufficient to find out the private key, the other key that is kept secret. So as I said earlier, public key crypto system can be used for confidentiality or secrecy. Imagine you have two parties, A and B. A is the source, B is the destination. And also imagine that there's a key per public key and private key of Bob. Public key of Bob is used for encrypting the original message X and creating this ciphertext. Then that ciphertext will be later be decrypted using the decryption algorithm and the private key of destination B to reconstruct message X. Also, as I said before, you can use the public key crypto systems for authentication and digital signature. In this example, let's say the message X is encrypted using the encryption algorithm and the private key of the sender or source, and the encrypted message is given to the destination, and destination who has the public key of source A applies the decryption algorithm on both public key of A and also the decrypted message Y, and it reconstructs X, and this way destination B knows that the message X is coming from the source A, not from anyone else. And that's basically the authentication process. Now, as I said earlier, this needs to be a bit more complex. What I mean is we need to send X as well along this encrypted part, Y, and also in practice, we are not going to apply the encryption algorithm on the whole message X for signature. We are going to apply it on the hashed value or the crypto hash value applied on X, so that we can save some time, because X can be very long, but the digest of X using a hash function, using crypto hash function, would be a constant size, and generally speaking, smaller piece of message, and that would save some time and energy when you want to sign a message. And that crypto hash function will be reused by the destination B when destination B wants to verify the signature. So imagine Y is given, what Y is sent to B. What B needs to do to verify the message is to basically apply the decryption algorithm on Y and public key of sender A to reconstruct the hash function or the hash value of X. And then because X is also given to destination B, it applies H on the given message X prime. Let's say the message that is received by destination B is X prime. A sends X, but B receives X prime. And if these two are the same, then destination B will know that message X is authenticated and no one has changed the message X after A has forwarded the message to B. And this way the authentication process gets completed. Now, in some cases, we need to have both authentication and secrecy or confidentiality at the same time. What does that mean? That means source A wants to send a confidential message to B, and also source A wants to authenticate the message by signing it. So we need to apply two encryption algorithms on the sending side and two decryption algorithms on the receiving side. The sending side has to first sign the message using sender's private key. Again, it may not sign X, it may sign H of X, which is the digest of X, but these are minor details. We don't really need to repeat them over and over. And then after that, the result of signing X will be encrypted using the public key of B, so that no one else can see that. And then we send the results through a channel, and this channel can be sniffed by anyone, and anyone but A and B are not going to be able to understand what the message is, because it is encrypted for confidentiality. When the receiver B receives it, it applies the private key, or his or her private key on the message, on the ciphertext Z, so that it can reconstruct Y. And after reconstructing Y, which is basically the signed version of the message, it can apply the decryption algorithm using the public key of the sender to reconstruct the message X, and this will tell B that the message is authenticated and A is the real sender of the message. Now, before we get into the details of a public key crypto system, let's find out what the applications of public key crypto systems are. Well, you can divide or classify the applications into three categories. One is encryption decryption for confidentiality, the most obvious one. Basically, the sender encrypt the message with the recipient's public key so that only the recipient of the message can decrypt the message using the private key that they have. The second one is digital signature for authentication. The sender signs a message with its own private key, and this way everyone who receives the message can authenticate the sender by applying the public key of sender on the message. And as I said, normally we sign the message digest. And also the third class would be key exchange for symmetric key distribution. When two sides wants to share a symmetric key so that they can create a communication channel encrypted by symmetric encryption, they need to exchange a session key, and in order to do that they use public key crypto systems. And some of the algorithms or some of the public key crypto systems are suitable for all these three classes or all these three types of applications. So, however, some others can only be used for one of the three applications or two of the three applications. So let's take a look at this table, which basically introduces four public key crypto systems and the applications of those algorithms or those crypto systems. The first one is RSA, which can be used for both encryption decryption for confidentiality. It can be used for digital signatures. It can be used for key exchange. The second one is elliptic curve cryptography or ECC, which can be used for confidentiality, digital signatures, and key exchange. Diffie-Hellman, a very historical algorithm, it can be used for key exchange only. And then DSS, which can be used for digital signatures. Now let's check out the general requirements of public key crypto systems. The first one is that it should be computationally easy for a party like B to generate a pair of public and private keys. So every party in the network can easily generate their own public key and private key. Second, it's computationally easy for a sender like A, knowing the public key and the message to be encrypted to generate the corresponding ciphertext. That basically means the encryption algorithm should not be computationally heavy. The third item here is it should be computationally easy for receiver B to decrypt the resulting ciphertext using the private key to recover the original message. So if you do have the appropriate key and the algorithm, you can easily decipher or decrypt the ciphertext to reconstruct the original message. This should not take a lot of resources. Moreover, it should be computationally infeasible. That means it should be very, very hard for an adversary knowing the public key to determine the private key. So if you know public key, that's normal. Everybody knows public key, but you cannot imply or find out private key given the you cannot imply or find the private key given the public key. That should be impossible. Also, Another thing that should be impossible for the adversary is that if the adversary knows public key and the ciphertext, original message cannot be recovered. That's the whole idea of confidentiality application of public key crypto systems. Also, the two keys that we use in public key crypto systems can be applied in any order. So you can apply the public key on a message, and then the private key should be able to recover the message, or you can apply it on private key, and then public key should recover the original message. As I showed you, for digital signatures and for confidentiality applications, we use two different orders of applying the keys, and both of them should work. Now, the very important requirement of public key crypto systems is that they need to have a trapdoor one-way function. First of all, in order to understand things, let's find out what does a one-way function means. This is kind of similar to the pre-image resistance feature that we saw for crypto hash functions. A one-way function is the one that maps a domain into a range such that every function value has a unique inverse, with the condition that calculation of the function is easy, whereas the calculation of the inverse is infeasible. Now, what does that mean? That means you can go from X to Y, from domain to codomain, or target, but you cannot go from target to domain. That means f of x is computationally easy, but f inverse of y, to reconstruct x, is computationally infeasible or very difficult. Now, in order to make a public key crypto system, we need to have a trapdoor one-way function. It's a special type of invertible functions such that if you know a piece of information, which we call it key, the f inverse would be feasible and would be easy to calculate as well. But if you don't know that key, it would be impossible or computationally infeasible to calculate the inverse of the function. So let's find out what trapdoor one-way function means formally. Y equals f sub k of x is easy if k and x are known. What is k? K is an extra piece of information that's called the key. So it's easy to find out y given the key and x. It's easy to find x given the key k and y. That's the trapdoor. So if you know the key and you know y, you can inverse f easily and find out x. What is not feasible, or what is not easy, what is computationally infeasible, is when you have y but you don't know k and you want to reconstruct x. So x equals f inverse of y with the unknown k should be infeasible. And all the practical public key crypto systems depend on a suitable trapdoor one-way function. So in this lecture, I'm going to talk about the details of an algorithm that is used for public key encryption, and that is called the RSA algorithm, which is the initial letters of three scientists who created this algorithm. It's the most widely used general purpose approach to public key encryption, and basically, if you want to briefly mention what RSA is, you can say it's a cipher in which both the plain text and ciphertext are integers between 0 and n-1, where n minus 1 is some semi-prime integer. A semi-prime integer is basically the product of two prime numbers. You know what prime numbers are. Prime number is a number that is only divisible by 1 in itself. And using prime numbers, we define semi-prime numbers, which are basically product of two prime numbers. And this semi-prime number n is typically 1024 bits, which is going to be about 309 decimal digits. So n is not a small integer. It's a very, very large integer. All right, so here is the RSA algorithm. RSA uses an expression with exponentials, and RSA use modular arithmetic. If I want to summarize what mod means before I explain anything else, I can say this. If you have two integers like a and b, then a mod b would be equal to a%b, which is the remainder of dividing a by b, if a and b are positive. The difference between mod and percent sign, which we all use in different programming languages, is that percent operator may result in a negative number, but a mod b is going to always be between 0 and b. Actually, it can be equal to 0, but it cannot be equal to b. So I should say it's including 0, but excluding b, from 0 to b minus 1. So when does this equation, or when is this equation wrong? A mod b is not going to be equal to a% b if a% b results in a negative number. But even if that's the case, we can relate the two values. We can say if a mod b is negative, then just add the negative value by b to construct or to calculate a mod b. So a% b may result in a negative value. If that's the case, just add that negative value by b to calculate a mod b. So you basically know what a mod b is. It's just very similar to the percent operator in different programming languages. Now, with this introduction to mod operator, let's move forward with the RSA algorithm. A plain text is encrypted in blocks. So if a plain text is very long, we need to break it into blocks, right? Where each block has a binary value less than some number n, where I told you before n is a semi-prime number, and the number of bits in that block should be equal to 1 plus floor of log n base 2. So that basically means if you convert n to binary and count how many bits it has, that should be the exact number of bits that every block of the plain text must have. As said before, the plain text should have a numerical value less than n. It can be from 0 all the way to n minus 1. And also, in order to do the encryption, let's say you want to do encryption for confidentiality purpose. You have a plain text with a certain block like m, and you want to construct the ciphertext block C given the plaintext block M. The way to do it is to raise m to the power of e, where e is going to be some part of public key of the receiver. And then find the mod of m to the power of e when it's divided by n, or find the remainder of m to the power of e when it's divided by n. That would be m to the power of e mod n. That's going to be your cipher text block. And then in the receiving side, the receiver knows his or her own private key. Some part of private key would be d, which is an integer. Then the receiver basically raises c, which is the ciphertext block, to the power of d, and then after that it finds the remainder of the result when it's divided by n, and that's going to reconstruct the message m. If you combine these two equations, you will get this equation, which is equal to basically m. The equation says m to the power of e times d mod n is equal to m, and this can be proven if you know a little bit of number theory, but I'm not going to go through the details of number theory. Just want to briefly tell you how RSA works, because the details of it wouldn't be part of this course. The details of it requires you to know a lot of number theory theorems that, if you're interested, you can check out online, but it's not going to be beneficial for this course. Just to summarize, the public key here is ENN, and the private key is DNN. I'll tell you what E and D are and how they get calculated in the next slides. So let's take a quick look at how the key generation step in RSA algorithm works, how encryption works for confidentiality purposes, and how decryption works for confidentiality purposes. Let's start with the key generation by the receiver. Let's say Alice, who is going to be the receiver of a message, is going to generate a public key and a private key. First, Alice selects two random prime numbers p and q that are very, very large, right? There should be so large that their product should be equal to an integer that is about 1024 bit long, which is, it's a very long number, like 309 digit long. So p and q, which are prime number, random prime numbers, are not going to be like a small prime number. They're huge prime numbers, and that's going to basically helps the security of RSA. If they're small, then RSA wouldn't be secure. And P and Q are both prime, and they're not the same. They're two different prime numbers. And then by multiplying P and Q, you get the value n for the RSA algorithm, and then you find the Euler's totient function of n, which is equal to p minus 1 times q minus 1. Now, totient function, which is represented by phi, is defined for every integer and is defined as the number of integers that are less than n, such that the number and n are relatively prime. Relatively prime means their greatest common divisor is 1. So these are some quite complex details about RSA that you don't really need to know. But anyways, I just want to briefly show it to you. After the totient function is calculated, you need to select an integer e, and that e is going to be some part of the public key of Alice. So how do you calculate e? E should be a random number that is relatively prime to the totient function of n. So the greatest common divisor of phi of n and e is going to be 1, and e is, of course, between 1 and phi of n. Now, because n is a very large number, phi of n would be very, very large number. But E is not going to be super large. I'll show you later the common values for E. That's going to be about 65K or so. Then given the value of E and the value of phi of n, we can calculate the value of D by Alice, which is going to give Alice a trapdoor. And knowing phi of n and E will make you able to calculate D, where D is part of private key that nobody needs to know other than Alice, but E is public information. So this calculation is impossible if you don't know the totient function of n, or you don't know phi of n. In order to calculate phi of n, you need to know the P and Q. So the beauty of RSA algorithm is this: everybody knows what P times Q is, but only the key generator, which is Alice, knows the values of P and Q. Now you may say, wait a minute, this is easy to do. If I know the product of P and Q, I can calculate P and Q. How? By doing prime factorization. Probably you have learned it in your early years of school. For example, if I give you the number 6 and I say, this is a semi-prime number, find out the prime factors. You just simply say 2 and 3. That's true, but if the number is astronomical, if the number is, let's say, if the product of P and Q is 1024 bits, you need years and years of calculation by a supercomputer to basically factor out that astronomical number n and find out P and Q. And that makes RSA secure, because prime factorization of a huge number, despite what you might think, is a very hard problem, and it's almost impossible to solve, because, you know, if you solve it, then RSA wouldn't be secure anymore, because everyone will have access to P minus 1 times Q minus 1 if you know P and Q. Everyone can calculate the totient function of n, and everyone who has totient function of n and the public key E, they can calculate D. And I'll tell you what E inverse means. E inverse is defined in a different way than what you can assume a reverse is. It's not a reverse of E. Basically, D, which is E inverse, is also a integer. It's not a fractional number. But anyways, the public key is E and N, the private key is D and N, and that's the key generation step that is done by Alice. Now, imagine keys are generated, the public key of Alice and private key of Alice. Bob wants to encrypt a message so that only Alice can see it. What does Bob do? Bob basically breaks the messages into smaller pieces so that each piece or each block of the plain text is less than n. As I said, the block can be like about 1024 bits, because n is 1024 bits. And then what Bob needs to do is to apply this operation on m, raise m to the power of e, and find the remainder when it's divided by n. You may say, these are huge numbers. How is it possible to raise a huge number to the power of e and then find the mod by another huge number? Well, these are possible with very few instructions and very fast operations, because of the beauty of number theory. We can use number theory to simplify all of these huge powers and huge remainders, and basically do the encryption very, very fast. And then that's basically what happens on the sender side, on the Bob side. the receiving side, where you have Alice, will decrypt the cipher message C to reconstruct message M. And to do this, Alice needs the private key, which is going to be D and N. So what Alice does is raises the ciphertext C to the power of D, and then find the remainder when it's divided by N, and that would reconstruct that block of plain text, which is M. As a very quick numerical example of RSA, think about the following numbers. Imagine the number n is equal to 187. That's n. And n is a semi-prime because if you do prime factorization for 187, you get 11 times 17. So basically, 11 is my p prime and 17 is my q prime. And this is a very simple example, that's why they're pretty small. And imagine that the plain text is 88, which is reasonable because plain text should be less than n, which is 187. And Bob wants to encrypt the message with this public key. The public key is 7 and 187. 187 was the n, and 7 is basically the variable e, which I showed you in the previous slides. And what Bob does, it raises 88, the plain text, to the power of 7. If you have a calculator, you can do it because that's not going to be a huge number. And then find the remainder when it's divided by 187. The result is going to be 11, and the 11 would be your ciphertext. Then on the receiving side, when Alice wants to decipher or decrypt this message, Alice basically says, why not applying the decryption algorithm, which is basically 11, the ciphertext, to the power of D, where D is equal to 23. And the result, mod 187, will reconstruct 88. Now, let me tell you the relation between E and D. If you remember, I said given n, you can calculate the totient function of n, which is in this case what is that? 187, right? And if you remember in the previous slides, the totient function in general is going to be equal to the number of integers that are less than n, or 187 in this case, and they are relatively prime to n, but when the number n is semi-prime, which means it's a product of two prime numbers, it's very easy to calculate. That's going to be equal to p minus 1, which is 10, times q minus 1, which is 16. When you simplify this, you get 160. And this 160 and E, which is equal to 7, can be used to calculate D on the Alice side, on the sender side, I'm sorry, on the receiving side, when Alice wants to generate the public and private key. So what I need to calculate is that 7 times D mod 160 is equal to 1. And that's the definition of inverse. I told you that D is going to be E inverse in base 160, in base phi of n. And the definition of this inverse is basically this equation. That basically means if you multiply E, which is in this case 7, by D, and find the remainder when it's divided by totient of n, which is 160, the result should be 1. And let's see if that's the case. In this case, I just want to show you that this is the case. So if I replace D, which is, if I replace D with its value, which is given, which is 23, and do this calculation of 7 by 23, let's do it right now. 7 times 23, the answer is 161. And the remainder of 161 mod 160 is equal to 1. That's why we say D is equal to E inverse. So although we call it E inverse, it's not going to be a non-integer value. It's not going to be a fractional value. That's the definition is basically if you multiply E and D, its remainder is going to be 1 when you divide it by quotient of n, which is in this case 160. Now let's take a look at a bit more complex example of RSA and see how an RSA algorithm can process multiple blocks. Here is the general approach. The first step in the RSA is to use some random number generator algorithm to calculate, or to, I should say, generate the values for E, P, and Q, where P and Q are two prime numbers, and E is basically the public key, or the first part of the public key. And then using E, P, and Q, we can calculate D and N. N is basically the product of P and Q, and D is going to be the inverse of E in mod phi of n, where phi of n is P minus 1 times Q minus 1. And that can happen, the private key calculation can happen when you want to decrypt a message. So let's not go to that step. Let's go from step 1 to step 2. When you want to have the public key, then public key is basically E and N, where N is P times Q. In step 3, the sender of any message, let's say any plain text message, will break the message into smaller blocks, let's say P1, P2, all the way to whatever Pn, let's say, and each of these P's are going to be less than or equal to n. If you think about each block as an integer, that integer should be less than n. And then we use the public key E to calculate the ciphertext of every plain text block. So C1 will be P1 to the power of E mod n, C2 is going to be P2 to the power of E mod n, all the way to whatever number of blocks are. Let's say Cn is equal to Pn to the power of E mod n. And then after calculating all the blocks of the ciphertext, we are going to transmit it to the receiving side. In the receiving side, we need to basically calculate the private key. As I said, private key is going to be D and N, and then recover the text by simply saying let's raise the first block of ciphertext C1 to the power of D, and then find the remainder when it's divided by N. That's going to give you P1, and then P2, P3, all the way to the last block of the plain text. Then you combine all those plain text blocks to reconstruct the original message. Now, here is a numerical value, the random number generator on the right hand side. As you see, I'm just going to show you a numerical example. The random number generator is going to generate the following random numbers. E is 11, P is 73, Q is 151. As I said, in real words, RSA's PQ would be about 150, 160 digit long. They're not going to be small numbers like 73 or 151. But these are okay numbers for this example. These are both prime numbers. The product would be 11,023. That's going to be the value n. And you can find out the quotient of 11,023 by multiplying 73 minus 1, which is 72, by 151 minus 1, which is 150. The answer is 10,800. So 10,800 is the quotient of 11,023. And then because E is 11, that's the random number generator outcome. The inverse of 11 mod quotient of n would be 5,891. You can verify it by multiplying 11 and 5,891, and then find the remainder of the product when you divide it by 10,800. The result should be 1. I'm not going to do it, but you do it if you're wondering if it's correct or not. In the second step, after generating E and N, we are ready to basically apply the encryption algorithm. So let's say the sender wants to send the following message: how are you? And how are you is going to be broken into its original characters, and let's say every character is corresponding to a number from 0 to um, 52, where um, the lower cases or the lowercase letters are from 0 to 25, and the uppercase letters are from 26 forward, and then you have white space, which is equal to 62, and question mark, which is equal to 66. It's kind of similar to an ASCII code, but it's a little bit different. Doesn't really matter how you encode a string. Like, this is a weird encoding, but we're gonna keep it as it is because it's gonna make things a little bit easier. Then we create multiple plain text blocks. Each one consists of 4 digits, and to create these blocks, we just concatenate two-digit numbers, let's say 33 and 14, which was encoding H and O, will create the first plain text block, which is 3314. The next one is 2264, which creates 2264. Now, all of these plain text blocks are going to be 4-digit integers, and that's a good size because our n is 5-digit long. So of course, all the p's, every pi is going to be less than n. That's crucial in order to have an RSA working. Now, in the next step, we're going to apply the encryption algorithm, which is every plain text to the power of e mod n, and calculate all the C values, all the ciphertext. And as you see, these ciphertext blocks are all less than n. And then after that, we're going to transmit the ciphertext blocks to the other side, and then we're going to apply the decryption algorithm on them. We're going to raise every ciphertext CI to the power of d, which was calculated as 5,891, and then we're going to find the remainder when it's divided by n, which is 11,023, and magically you see that we get the same exact how are you question mark message after it's encoded with that weird encoding that I explained. And basically that's a very simple example of RSA when you process multiple blocks. So a very important part of RSA and many other public key crypto systems is to generate a random prime number. In order to generate a random prime number, there are many algorithms that are, suggested by many great scientists and mathematicians and number theoreticians. I'm just going to tell you the most commonly used one, which is the Robin-Miller test. So this is a algorithm to generate a random prime number, which is used for RSA for generating P and Q. Imagine you want to generate a random prime number with n bits. The first thing you need to do is to generate a random n-bit odd number. Why should it be odd? Because obviously if it's even, then it's not going to be prime, because the definition of a prime number is that it should not be divisible by any number but one and itself. And although 2 is prime, but 2 is not 2 does not matter, because when I say a prime number, I mean an n-bit prime number, when n is a very big number. Now, after you generate that random odd number, you need to ask yourself, is this divisible by the first few prime numbers like 3, 5, 7, 11, 13? Those are small few prime numbers that we know at the beginning of the list of all prime numbers. If that's the case, then that means the number is not prime because divisible by 3, 5, 7, 11, or some small prime number. That means let's generate another number. But if it's not divisible by those few prime numbers that we know, then we can run a Rabin-Miller primality test. And that primality test is going to make us a bit more confident that this number is prime. It's not going to make us 100% sure that this number is prime, but it's going to give us a lot of confidence in terms of probability. I couldn't say 100% confidence, but let's say 95 or 99% confidence that the number is prime. So this is the Rabin-Miller test. You need to find some integers like k and q such that q is odd and n minus 1 is equal to the power of q to the power of k times q. What does that mean? That means because n was odd, n minus 1 is even. Now, factor out k2's from it, or factor out as many 2's as you can from it. Let's call that number of 2's k, and then the remainder is going to be prime number, an odd number. That odd number is going to be called q. Then select a random number a from 1 to n minus 1. When I say random, I mean just uniformly random number. And apply the following steps on it. First, raise a to the power of q and find the remainder when it's divided by n. And if it is equal to 1, then you say the test has been passed. So we just return inconclusive because we cannot say 100% the number is prime, but we can say the Rabin-Miller test has been passed for this particular instance. If the remainder is not equal to 1, then we get into this for loop, and for j from 0 to k minus 1, we do step number 5. In step number 5, what we do is we raise a, that random number, to the power of j times q, and then you find the remainder when it's divided by n. If the result is n minus 1, then that means the test is passed, so you return inconclusive. If you never pass the test in step 5, then you go to step 6. In any of the iterations of step 5, then you go to step 6 and you return composite, which means the test has been failed, and you need to pick another number. So when you're performing the Rabin-Miller primary test and it is passed once, you need to try it 19 more times. So you need to try it a total of 20 times. Every time that you run the Rabin-Miller test, you're going to pick another random integer, a. And when Rabin-Miller test passes for a number that you generated randomly 20 times, then you can say with a very high confidence, you say that number is going to be a prime number. That number n is going to be a prime number. Now, if any of these 20 iteration fails and one of those 20 Rabin-Miller tests fails, then you need to go all the way up to the very first step and generate another random number. And you continue doing this until you run Rabin-Miller 20 times and it all passes. If it all passes, then the algorithm is over and you generated your prime number. Now, as the optional part of this lecture, let me briefly explain how to calculate the inverse of E mod the torsion function of n. So this is useful when you want to calculate the private key given the public key E and n. So the private key is D and n, and D is going to be the inverse of E mod phi of n. In order to do this calculation, we're going to use something called some algorithm called extended Euclidean algorithm, which is a very fast algorithm. It's going to be a linear algorithm that can calculate D. The idea is this: because D is equal to E inverse, D times E is going to be equal to a multiple of phi of n, which is k times phi of n, and then added by 1, because the remainder is going to be 1 when you divide it by phi of n. Now, if you simplify this, you get this equation, which is d times e plus minus k times phi of n is equal to 1, and 1 is basically the greatest common divisor of e and phi of n. And in number theory, there's an algorithm that can calculate the value of d and the value of negative k given the values of e and phi if 1 is equal to the greatest common divisor of e and phi of n. So let's consider e to be b and phi of n to be a and negative k to be x, which is the coefficient of a, and d to be y. So I'm just going to calculate the value of x and y. Mostly, I don't care about x, I just care about y. So that, ax plus by is equal to 1, right? That's what I need to calculate. And as I said, 1 is basically the GCD of a and b. Now, this is the extended Euclidean algorithm. It's a very common algorithm in number theory. The idea is very simple. Let's say you have these initial values for ri's and xi's, and basically, r negative 1 would be a, r0 would be b, x negative 1 is 1, y negative 1 is 0, x0 is 0, and y0 is 1. And using these base cases, we use these two recursive relations and these two recursive relations, total of 4 recursive relations, to calculate R1, R2, R3, R4, all the way to Rn. Just to briefly tell you what they mean, basically every Ri is going to be, let's say R3, right? R3 is equal to the remainder of dividing R1 by R2, and the Q3 is equal to the quotient of the same division. And you can do this many times until you reach to a remainder equal to 1, and that's when you should stop, because you reach to 1, which is in this case the GCD of a and b, equals a times xn plus b times yn. So from here you can conclude that you can conclude that xn is basically the coefficient of a, and yn is the coefficient of b. Now we were looking for d, which is the coefficient of b, where e was equal to b, and you can calculate d by just saying d equals yn. What is yn? Yn is the y in the nth step, which is calculated by this formula, and the nth step is the step where Rn is equal to 1. So it's a little bit complex, but if you write down the formula in a Python or Java or any other programming language, it's going to take the computer very small fraction of time to do this calculation. Just to show you how easy it is to calculate E inverse to reach to D, I have used a very simple Excel sheet that basically um, implements the extended Euclidean algorithm and all those recursive relations to find out that 11 inverse mod 10,800 is equal to 5,891. That's the number that we saw in the previous numerical example. Before we close the RSA algorithm discussion, let's find out the very last piece of puzzle, which is the way to compute a to the power of b mod n, where b is a very long number and possibly, you know, a can be a very long number, and also n is a very long integer. So we're going to raise a to the power of b. We're going to find its mod when it's divided by n. We're going to do this very quickly. How is it possible? Imagine you have represented integer b using k plus 1 bits in binary, right? bk minus 1 all the way to b0. bk is the leftmost or most significant bit. b0 is the least significant bit. In order to calculate a to the power of b mod n, we have a very simple linear algorithm that just goes over all the bits of b from left to right, from k to 0, and it does the following operation. First, imagine that the integer f is initialized to 1. That's basically the return value at the end. And also c is set to 0. In each iteration of this for loop, you need to double the value of c and set f equal to f squared mod n, which basically multiplying f by itself. Find the remainder by n is going to give you the value. And then ask yourself, is the next bit of b equal to 1? Is bi equal to 1? If that's the case, increment c, do c++, and multiply f by a, and then find the remainder when it's divided by n. That's going to give you the new value for f. Do this until you reach to the very last bit of b. When you reach there, then f is going to be the final value of the remainder, and that's going to be the end of the algorithm. So let's see an example of a fast modular exponentiation algorithm that I showed you in the previous slide. Imagine that you want to find out the remainder of 7 to the power of 560, which is a huge number. When you divide it by 561, and you want to find out what's the remainder is. The remainder, based on a very famous number theory theorem, is going to be equal to 1, but let's say we don't know that. We're going to calculate it. Here is how we can use the fast modular exponentiation algorithm. We're going to first write down b, which is the exponent, as a binary number, and then representation of 560 binary would look like this: 1000 110000, and then we write it in the first row. The second row will keep track of c, which I showed you in the previous slide as one of the variables of the algorithm, and the last row is going to be f, which is going to eventually be equal to the remainder. As you may remember in the previous slide, f each time is going to be squared, and like in this case, 7 squared is equal to 49. And if the current bit is 0, we only square it. If the current bit is the current bit of b is not 0, if it's 1, then not only we square it, but also we multiply it by a, which is the base of the exponential relation. In this case, a is 7. So that's basically the case, and you can just fill out this table using a very simple Excel sheet. And at the end, when we reach to the last bit of B, you can reach to the final value of the remainder, which is 1. So as you see, we have correctly reached to the actual value of remainder, which is 1. Now, this is the end of RSA discussion. Why did we talk about all these complex parts of RSA? The reason is I'm going to show you. I have shown you that RSA has a lot of complex calculations. Although we are using very smart algorithm, but still calculating the parameters of RSA is computational. It's computationally heavy, and it's not very efficient. So instead of RSA, in modern days, we use another public key crypto system, which is called ECC, elliptic curve cryptography, which is going to be more efficient compared to RSA. So in the next discussion, you will see examples, or you will see the details of ECC and how it's faster compared to RSA, but it offers the same kind of security. Finally, you can see my reference for this lecture, the Cryptography and Network Security Principles and Practice, William Stallings, 7th edition, Pearson, 2017.